Okay, so now, all right, good afternoon, everybody. This is Alejandro Sznakovsky, and this afternoon, as Tracy introduced me, we're going to be discussing about the fundamentals of power transformer protection. We apologize for that small glitch that we had a few minutes ago. It was onto a couple of slides, though, without realizing that my phone was mute, but hopefully we won't run into any further problems. We encourage you to use the questions interface on your GoToWebinar, dock in your computer, so that if you're having any type of audio problems, please let us know, and we'll take immediate corrective action. So thanks for those of you that brought this up to our attention. So as I discussed, we're going to dive into the fundamentals of power transformer protection. We're going to talk a little bit about construction and some of the fundamentals, though, of transformers overall. We're going to discuss three-phase transformers, connections, and vector group, and how some of these attributes affect the protection of the transformer. We're going to discuss some of the transformer faults, and how do faults inside of the transformer occur and evolve. And then we're going to finally talk about, protection of transformers based on microprocessor multifunction device. And I just make that, that clarification, because a lot of these elements are only possible, though, based on, advanced numeric techniques, though, that are only enabled with the utilization of microprocessor devices. So we'll discuss differential protection mainly, and then we'll discuss some backup functions, though, related to, overcurrent principles, though. Last but not least, we will also have a discussion about inrush current and overexcitation, and how those two conditions affect and need to be accounted for in differential protection schemes of transformers. Okay, so with that in mind, let's go ahead and get started. So as most of you know, the power transformer is a very, very, very key and important element within the power system. So, and essentially, what it allows us to do mainly, it's really power transformers enable more efficient transfer of bulk power. So when we, basic principle, though, or within the context of this presentation, though, one of the basic functions, though, of the power transformer is to step up voltage, though, to a level that's high enough in such a way that you can carry more real power flow through a particular corridor, though, without having to send as much current as you would otherwise would have to with a lower voltage. What that allows us to do is to have, reduce our resistive losses, though, over that particular transmission line. Thus, we're able to transmit power in a more efficient manner. That's why when we look at the four, most typical arrangements that we have, that we find transformers applied in the power system, though, we have step-up transformers, which will take a lower voltage, which will interconnect a lower voltage system with a higher voltage system. One case would be in generation. Perhaps you have, generator, though, that you want to connect to the transmission system. Generators, because of design constraints regarding insulation and personnel safety, cannot have ratings of very high voltages. So that's why, generators typically have rated voltages, though, on their terminals below 13.8 kV. But as we know, transmission systems, though, are typically in the order of 115 kV and above. So if we need to interconnect those two systems, one that is in charge of the strip of delivering power and another one that's in charge of generating the power, we need a transformer, which will in turn take this power, which will in turn connect these two systems. Second one would be a step-down transformer, which we actually have the other end of that particular that particular topology, though, where we now have a transmission system that we would like to connect to a distribution system, which, you know, lower voltage level, though. So then we need a device that will interconnect those two networks and step down the voltage from a particular voltage level to another voltage level. An example of that would be a 230 kV to 13.8 transformer, or 115 kV transformer to 13.8, and so on. Third type that's also commonly found would be an auto transformer, okay, which is, you know, from a transmission network perspective, it's a device that's usually utilized to interconnect two transmission voltages, though, or two transmission networks that are operated at two different voltage levels. So, for example, if a utility operates a 400 kV loop and they also operate a 230 kV loop, and you wish to connect those two networks, typically you would utilize an auto transformer, or perhaps a Y-to-Y transformer from that perspective, though, which will allow to connect those two voltage levels, though. And then under certain scenarios, though, a grounding transformer, or what's also commonly known as a zigzag transformer, could also be applied to provide a source of zero sequence currents and grounding for a particular network. There's other types of transformers that are utilized and that are utilized. You also have power reactors, though, that are utilized to provide reactive power, though, injection onto the power system. You also have phase angle regulating transformers that aid on controlling power flow between 2 points within the network, and so on. But, you know, this is, you know, again, as mentioned, very, very important component, though, of the power system, though. As being a very important component of the power system, though, and, you know, as being a very, you know, size-wise, a very big device, though, it's a very expensive, though, piece of equipment, though, and a very critical piece of equipment, though, because it is something that, given its size and its weight, it's not something that can be manufactured pretty quickly, and it's not something that can be mobilized or replaced pretty quickly. So it is very important, though, to protect the transformers, and when faults inside of the transformer do help, it is extremely important to try to mitigate the damages, though, so whatever repairs need to be done on the transformer are performed as fast as possible. A couple of points here, though, again, you know, repairs take a long time, and also given the size and the transportation cost and limitations, though, it's not easy, though, to replace a transformer, though. So there's a lot of considerations on that front. That's why not only the protection, but the monitoring of the transformer to ensure that it is running, you know, that it's running properly, and we don't have a run to failure type of scenario, though. It's maintained. This is now just a review of the basic transformer model, though. Okay. You guys can see the mouse perfectly, see the pointer. So basically you have a core. In the case of power transformers, you have a core, which is usually made out of a soft steel, providing a path of low reluctance, though, to the flux. You have one winding, okay, that's connected to a particular voltage level, and then you have another winding which is connected to another voltage level. You could have 3 winding transformers, in which case you would actually have 3 windings connected one on top of the other, and we will see a picture of that in the next slide. This is just a basic representation of a single-phase transformer where you essentially have what's known as an ampere turn balance, where the primary current times the primary winding turns must equal your secondary current times your secondary turns of that secondary winding, though. Then impedance-wise, it's important to recognize some of the elements, though, that play around. Ultimately, you know, from an electric circuit perspective, though, the transformer represents an impedance. as such, it needs to be properly modeled though on any type of, of fault analysis type calculation though. Essentially what we have though is you're going to have an impedance, primary winding, an impedance associated with the primary winding, which is the ZP. This ZP is the leakage reactance of winding 1 plus any type of resistive losses though on winding 1. The S, it's your secondary winding impedance though, which again, it's winding 2 leakage reactance though, plus any type of resistive losses associated with the secondary winding. And then this branch right here is something that's really important to take into consideration though, as we will find out during our extended discussion of differential protection, where this is your magnetizing branch or your magnetizing losses though, which they're known as your, your copper and your iron losses though. Some of them are accounted by the eddy currents that are induced in the core of the transformer though. Some of them are associated though with the copper losses though of the core as well. Okay, and we could see that as IH and as an IM being your core plus your magnetizing losses. This is now a picture though, or of a power transformer, and there are some elements though that are worth mentioning though. First and foremost, we have this big, towers though, which are your big insulators or your high voltage bushings though. So in this particular case, these are isolators or bushings that provide proper isolation though, or insulation from this point onto the tank of the transformer, which sits at ground potential. So the idea is that the creepage distance though of this, as well as the insulation strength of the bushing, should be sufficient so that you don't have a flashover between the conductor, the primary conductor that's connected to this particular point, and the tank of the transformer. Equally, but it's not as easily seen in this particular illustration, we have a smaller bushing, which would be the low voltage bushing of this particular transformer. And it's a smaller because you need a smaller creepage distance because the voltage is less, thus you don't need as much of an insulation strength though, since the voltage of the line is smaller. Here, a couple of other components though that are important to mention. You essentially have the radiator of the transformer though. Usually on some models you just have a radiator though, and then there's going to be fans and cooling mechanisms though that maintain the temperature inside of the transformer to a particular, within a particular range. Okay, and then number 9 here, this is something that's very important to recognize, and this is just an oil reservoir though, where excess oil is stored here. It's important that to consider the most power transformers that are in operation though are oil insulated. So what you're going to have, and I'm going to go back to the slide, to this slide that I have, you essentially have your winding, you have your core, and that's essentially inside this metal enclosure, okay? And that metal enclosure is filled with oil, and that oil is circulated and cooled via the radiator to maintain a normal temperature operating, at a normal temperature though, within the operation. Obviously, the temperature inside of the transformer, it's a function of a couple of things. It's a function of the ambient temperature, the temperature outside the transformer, and it's also a function of the current that's going through the transformer. Okay, the more current that's going through the transformer, or the more power that's flowing through the transformer, the more losses, and the more the more RI square losses that are associated with that equation, the more energy that's dissipated within the transformer, and that energy is dissipated in the form of thermal energy, which in turn results in a thermal rise inside of the transformer. You essentially, on that particular point, you essentially have, a balance between the cooling system of the transformer and the power that's flowing through the transformer to keep that thermal rise to a particular level. If that thermal rise continues to go up and continues to go up, then it's not only pressure though, but damage that can occur of some of the elements though that form the transformer though. So important point is, transformers have a certain, thermal operating ratio, that rating that's associated with the amount of power and the ambient temperature though, and those thermal ratings cannot be exceeded. And we'll have some discussions about that later on in our presentation. Now, for a view of, this is a view of the core inside of the transformer, or what's actually inside this metal enclosure. And what you're going to find is the following. You have a metal structure, okay, with several, layers. This is the core, and the core is laminated to reduce or minimize the amount of eddy currents, though, the amount of losses, though, as far as from a transformer design perspective, though. Okay, and then you could have multiple legs inside the core. The design of this core, I think I have a couple of pictures, though, moving forward that provide a good visual on that. But in essence, though, you're going to have each winding for, each winding for each phase, though, it's going to be wrapped around the core of the transformer. And in this particular case, this is a two-winding transformer. And here we could see how there is insulation between the core and the winding, and then there's actually insulation from turn to turn. So this is something that's very, very important. You have insulation between the windings and the core. You have insulation between high voltage and low voltage winding, and then you have insulation from turn to turn. Okay, so you have to keep that in mind when we start discussing transformer faults. Why this is important. It's also important to keep in mind that the core of the transformer is at ground potential and it's connected to ground. So, for instance, though, if for some reason you have a breakdown of the insulation between the inner winding and the core, you essentially now have a short circuit path through the core of the transformer through ground. So keep in mind this cross-sectional cut of the construction of the transformer when we start discussing internal faults and failure modes inside of this important apparatus. Now, let's talk about three-phase transformers and some of the special considerations. So one of the special considerations, though, is that need to be taken into consideration is the number of windings, whether you have 2 windings or 3 windings. In this particular case, we are actually just showing 2 windings, okay? And you could see that there's actually a total of 6 windings, primary winding for phase A, primary winding for phase B, and primary winding for phase C. And then you have secondary for phase A, secondary winding for phase B, and secondary winding for phase C. If you were to have a 3-winding transformer, then the arrangement would be the same, but with an additional winding wound around each one of the legs of this particular core, this particular 3-legged core. And then the other thing that we need to take into consideration is the electrical connection of the windings. You probably have heard about the term, delta connection versus Y connection, grounded Y connection, and so on. And there is an impact that there's, depending, based on that connection, we need to take that into consideration for the protection of our transformer. Okay. Here's just an example of some winding arrangements, though, for power transformers. We have the case where we have a YY 2-winding transformer here in the top left-hand corner. We have the case of a Y delta transformer, two-winding Y-delta transformer. Then we have the case of a delta Y transformer, okay? Here we have the example of a shunt reactor, okay? And we have three-winding transformers, and then we have the case of an auto transformer, okay? And again, we could see in the case of the auto transformer, though, what makes the auto transformer different from a regular transformer is that the transfer of power, though, from winding 1 to winding 2, or high voltage winding and low voltage winding, it's not just because of electromagnetic coupling, but there's also because of magnetic coupling, but there's also some electrical coupling, though, because the way this winding, though, this series winding is tapped. Okay. Let's actually go ahead and take a couple of minutes, though, to take on some questions, though. Let's see if there's no questions. Okay. No questions yet. Good. All right. So let's go ahead and take a look, though, at a basic three-phase transformer and some of the nomenclature as it applies to the ANSI world. First thing that we're going to find is, from an E-cleave perspective, you're going to have on the high voltage winding, it's referenced, though, the point of connection for polarity for phase A is referred to as H1. For phase B, high voltage winding, the polarity point would be referred to as H2. And then the polarity point for high voltage winding for phase A is referred to as H3. And then the neutral, if applicable, though, is referred to as H0. Similarly, our low voltage winding, though, polarity for phase A is going to be referred to as X1. Polarity of phase B of low voltage winding is referred to as X2. And then polarity of phase C, low voltage winding, is referred to as X3. And then the neutral point, similarly, is referred to as X0 of the low voltage winding. If a tertiary winding is present, then the way the nameplate information will be represented, though, for the polarity point of connection, they would be marked as Y1, Y2, Y3, and Y0 if a neutral connection point is applicable, though. Similar to, high voltage and low voltage, though. So high voltage H, low voltage X, tertiary Y. Okay. Oh, we got a question here about this slide. Right now, we are now just providing a description, though, of the point of connection, though, from a winding polarity perspective, though. We're not discussing the external connection of the transformer to the outside world. We'll discuss that in the next couple of slides. Now, ANSI standard for phase shift, though. So the ANSI standard for phase shifts is as follows, though. You're always going to have a relationship where the high voltage winding leads the low voltage winding by 30 degrees. So again, high voltage winding leads low voltage winding by 30 degrees. In the case that we just taken into consideration the nomenclature that we just discussed of H and X, then we will find the following configuration on a delta Y or Y delta type winding arrangement, where H1 is going to lead X1 by 30 degrees. H2 is going to lead X2 by 30 degrees. And H3 is going to lead X3 by 30 degrees in a case of a delta Y or Y delta transformer type connection. In the case of delta delta or YY connected transformer, there is no phase shift. Thus, you could see that H1 and X1 are in phase, H2 and X2 are in phase, and H3 and X3 are in phase. Take also note that the vectors for X in relationship to H are slower, indicating that X it's on a lower voltage magnitude. So now let's go ahead and discuss the our H and X naming nomenclature, though, with specifying the connection of the transformer. So we have here the first case where we have a Y connection. And a Y connection can be identified. Number one, there's not going to be any phase shift between this EMF or the voltage, though, between H1 and H0 versus the voltage between X1 and X0. And you can see that on both high voltage winding and low voltage winding, we have a connection where polarity is connected to phase A on the system, polarity mark is connected to phase B on the system, and polarity is connected to phase C of the system. And then the non-polarity legs, though, of each winding are all tied together and connected to neutral or ground. Same can be viewed, though, on the secondary or low voltage winding, though, where we have a YY connection. Now, when we talk about phase shift, though, what we have on the phase shift, though, is we are essentially we are essentially playing with the connections between each particular winding, though, to create, though, to combine the vectors, though. So this picture, though, this particular slide does a better job than the other one, though. We have a Y delta connection. So we could see that on the Y side, again, everything, the voltage, though, here on this winding connected on Y in relationship to the voltage, though, connected on the secondary winding. Take a look and see that in this particular winding, we have the non-polarity, the non-polarity lead of phase A winding is connected to the polarity lead of phase B winding. Okay? The non-polarity lead of phase B winding is connected to the polarity lead of the phase C winding. And then the non-polarity lead of C winding is connected to the polarity lead of phase A winding. And essentially, if you do a Kirchhoff's law equation of this, you're going to find that the current that flows out of X1 is going to be equal to the turns ratio times phase A minus phase C. And if we do the vector plot of that of the subtraction of those two vectors, we're going to find that this is a vector that lags the voltage across H1 and H0, or sorry, the current that flows through phase A high voltage winding by 30 degrees. And that all comes because of this vectorial addition, though, where here we have the voltage of phase A. We are connecting it with the non-polarity leg of the C winding. So we grab C, which is at 120 degrees. We rotate it by 180 degrees. We have now here this minus A. And then we just add these two vectors, and their resultant is a vector that's going to lag our vector at 0 degrees by 30. Okay? There's also a difference of magnitude, though, of the order of square root of 3, and this is just the result of the subtraction of those two vectors. Okay? Some comments, though, on this particular connection, though. One of the things about delta connections is that they provide means to isolate zero sequence network, though. It serves as a mean to isolate the zero sequence network of one portion of the system with a zero sequence network of another portion of the system. And what I mean by that is, if you have a phase to ground fault on the Y side of this particular transformer, there will not be any zero sequence contribution, though, from the X side winding of the system, from this particular side of the system. And the reason for that is because the zero sequence will actually be, the zero sequence current will be trapped inside the delta and will circulate for the duration of the fault. So again, it's a means to, provides means to segregate it, to separate the zero sequence network though between two systems though. Also, from a turns ratio perspective, though, our effective turns ratio, though, it's now multiplied by square root of 3. So effectively, though, you can actually manufacture, build a transformer that has an effective ratio that's higher without utilizing, though, an actual copper turns ratio that has that same magnitude, though. So you're essentially boosting your turns ratio, though, by square root of 3 of that front. So that's also another advantage or another reason why such connection is employed. This connection, by the way, in this particular case, where the Y side, leads the load side, the low side, or the delta connected load side, it's a connection that's primarily utilized in step-up installations, though, where the Y side is going to be connected to the transmission network to provide a source of zero sequence currents, though, so that phase-to-ground faults can be easily identified on the transmission network. And then the delta connection, though, it's utilized on the generator side of the equation, though, so that, again, we provide that isolation, though, between the zero sequence networks in such a way that if a phase-to-ground fault occurs within the generation station, though, the transmission network does not become a source. And this is a decision that's made because, as we've discussed on other webinars on this series, most of the faults are actually phase-to-ground faults, though. Okay. Here we have similar arrangement, but now the delta connection sits on the high voltage winding. So now we have, in this particular case, it's not phase A connected to the non-polarity leg of phase C, but we actually have phase A connected to non-polarity of phase B. We have phase B connected with non-polarity of phase C, and then we have phase C connected to non-polarity of phase B. And this is what's known as an A minus B delta, which in turn results in a connection where this winding will lead the low voltage winding, or the Y connected winding, by 30 degrees. The details, though, still apply. The need to, separate this two zero sequence networks, though, and an effective turns ratio, though, that's effectively higher by square root of 3. This particular connection, where the delta is found on the high voltage winding and the Y connection is found on the low voltage winding, it's typical of subtransmission or distribution step-down transformers. So, where to the particular distribution substation you have 138 to 13.8 kV transformer, 13.8 kV being a distribution level voltage, though, and this particular transformer will provide that transformation from a higher voltage to a lower voltage. The Y connection is on the distribution side, so there's a healthy source of zero sequence currents, so that phase-to-ground faults or faults involving ground can be easily detected, though, within that particular network. And this is very, very extremely common arrangement, though, utilized here in the United States, though, for our distribution systems, though. Now, one of the questions that we often get a lot is, so how is this, how is this phase shift, documented, and how do we determine, though, which phase shift to employ? And the phase shift is important, though, because even though both of these phase shifts, though, from an ANSI perspective, still the high voltage winding leads the low voltage winding by 30 degrees. Take note that in the case, or in this particular case, we have an A minus C, what's referred to as an A minus C delta in the case of the step-up transformer. And then in the case of the step-down transformer, we actually have an A minus B delta. And that would obviously have an impact, though, on differential protection when we are comparing, though, the currents from one winding with the currents from another winding. So one way that this is all documented is using the vector group clock system, where the high voltage or the reference winding assumes the 12 o'clock position, the rotation of the phasors is in the counterclockwise position, and then the low voltage winding, though, is the type of connection is referenced to with a letter. It could be Y or D, lowercase letter, and then it's followed by a number which will indicate the position of that particular vector in relationship to the start position or the 12 o'clock position. So in this particular case, we have a YN-D1 transformer. Y being the high voltage being Y connected, and then the D to document the low voltage winding, which is connected in delta, and it has the 1 o'clock position in such a way that the high voltage winding is leading the low voltage winding by 30 degrees. Each hour on the clock represents a 30-degree phase shift, though. So again, higher case, the capital letter, though, Y represents the 12 o'clock position. Lowercase letter represents any of the following position, and then the number that follows the lowercase letter signifies the position of that particular winding in relationship to the 12 o'clock position. In this case, 1 o'clock being 30 degrees lagging the 12 o'clock position. In this particular transformer, the high voltage Y winding is leading the low voltage delta winding by 30 degrees. In this particular case, though, we have another one, though, where we have a DYN1 winding, though, or transformer, sorry. So the D in capital letters, it's our 12 o'clock position, okay? And then our Y, our low voltage winding is a YN1, and then again we have our Y with this particular position, which is again it's the 1 o'clock position, meaning that the low voltage winding it's lagging the high voltage winding by 30 degrees. And then we have a third case where we actually now have a 3-winding transformer, where again high voltage is a Y winding in the 12 o'clock position. Low voltage is a Y winding, okay? So YY is, on the same, it's essentially in phase. And this is actually a mistake on this particular slide. It should be YN, YN, not YN, YN1. And then we have parentheses to illustrate the tertiary winding, and that's D11. In this particular case, the delta, it's actually leading the high voltage winding by 30 degrees. Thus, it's at this particular position in the clock. Now, what are some of the common failures, though, that are actually recognized, though? So transformer faults. Well, several of them, though. You could have turn-to-turn insulation failures, though, and again, just I'll refer you back to the slide where you have the cross-sectional cut of the different windings, that you could very easily see that you can actually have, if a breakdown of insulation occur between those two turns, then a short circuit could occur the two turns. Okay, and we'll talk a little bit later, though, as to why that is a hazardous condition, though. Okay. Think of some of these failures, though, as the result of the following. Some of the insulation, though, in these transformers could be in the form of some sort of varnish, though, or some sort of, resin, though. And as you could picture any of this varnish or resin type, type components, so they're pretty, relatively speaking, though, they're brittle, or they become brittle over time. So when through faults occur, or when the transformer is stressed, there's not only electrical effects, but there's also physical movement, though, because of the magnetic forces, though, that are involved with high levels of current. So each time that these things occur, though, there's contraction and expansion, though, of the windings, and each time those, that movement of the winding occurs, is just bigger chance, though, that this that the insulation, though, between windings or between turns can start to break down, though, and give in, and in turn, provide a path for an electrical short circuit between, either winding, core, or turn to turn. You could also have issues or breakdowns due to moisture, okay, deterioration, as I just described, face-to-face and ground faults. And then you could also have external faults, which due to the thermal as well as mechanical stresses, though, they evolve into internal faults inside of the transformer. These are mainly, winding faults. Then another type of faults that are, that need to be taken into consideration are faults inside the tap changer. So the tap changer is a mechanical device that essentially has the capability of changing the turns ratio relationship of the transformer so that the voltage can be regulated, though, on one of the windings of it, though. And the issue with this is that, you have, again, essentially a mechanical mechanism that is changing this turns ratio relationship. And inside of this particular mechanism, there, that's a particular source of faults as well. Oil leaks, overheating, electrical short circuits, or mechanical failures as well. From a bushing perspective, though, aging, contamination on the insulators, which in turn, create electrical faults similar to, contamination of insulators inside a transmission line, cracking, flashover due to animals, moisture building up on the insulator, thus creating, a flashover. Bushings are oil filled, so if you have low oil level, though, in turn you are, reducing the insulation strength of the bushing, which in turn can result in faults. And then you also have just damage of, actual physical damage of the bushing, though, due to earthquakes, objects thrown at the bushings, and so on. Core failures, you could have core insulation failures, similar to what we discussed with the windings, ground strap being burned away, loose clamps, bolts, wedges, and most of these as the result of the mechanical movement due to mechanical forces involved with magnetic forces involved with high fault currents. And then you have miscellaneous failures, those such as failure of bushing current transformers, metal particles in oil, damage during shipments, external faults, which in turn evolved into internal faults, poor tank welds, overvoltages, overloads, and so on. So these are just some of the causes, though, of transformer failures, though, which they could either be the result of mechanical mechanical forces, though, or electrical forces, though, inside the transformer. And here's just a breakdown, though, for the IEEE guide on protection of power transformers, and these are just some industry statistics related to the causes of failures of transformers. So 55% of the reported failures are winding failures, 21% type changer failures, 10% bushing failures, and so on. So what are some of the requirements for power transformer protection? Well, it should trip during short circuits, though, and ground faults, though, inside of the power transformer bank, okay, tank, I'm sorry. And in some cases, depending on the settings that are, depending on the scheme, though, it's also important to trip at external faults to provide fast backup protection. Again, we're discussing multifunctional microprocessor relays, which most of the ones that are available in the market have this capability. So we have essentially divided our requirements in 2 points. we have we essentially have short circuit protection, okay? And then on the second part, we have alarm or trip during abnormal conditions, though. And this could be as a result of overloading, exceeding or getting near to the thermal limit of the transformer, reduced system voltages, overexcitation. So these are more of monitoring, low speed, low reacting functions that will monitor the transformer over time, and if the conditions are adverse enough, we will make a decision to disconnect the transformer to avoid any type of damages to it. In the case of the short circuit protection, this is typically high-speed protection, though, because once a fault occurs inside of the transformer, the amount of damage is proportional to the energy of the incident. The energy of the incident is proportional to the amount of time that particular fault is occurring, though, inside of the transformer. So the faster we can isolate, we can electrically isolate the transformer, the less amount of damage, less repairs, and so on. Now, how are faults detected inside of the transformer? So now we, here I just have a quick overview of some of the different elements, though, that are utilized for transformer protection. So in the case of face-to-face faults, transformer differential protection at the top of the lids, Buchholz relays in the case of internal faults that occur below the oil level of the transformer. Essentially, the way a Buchholz relay, or what a Buchholz relay is a mechanical device that usually when faults occur, there's a breakdown of the oil inside of the transformer, and that breakdown of the oil results in gases being released. And this device is essentially a floater type that when this breakdown of oil occurs and this releasing of gas occurs, that gas is going to come up to the surface of it's going to come up to the surface though of the level of oil, and this particular device is essentially monitoring though for those bubbles coming up, and if the flow of the oil is severe enough, then it's an indication that gas has been released within the tank, indicating that a problem has occurred within the transformer. So it's also known as a flow type. It's a flow type relay because it essentially monitors the flow of the oil inside of a transformer. Though provides good, to a certain extent, though, provides good good sensitivity, since when any type of electrical fault occurs, there's going to be this breakdown of oil. So this is not an electrical or a microprocessor device. This is a mechanical device, so that's built in as part of the construction of the transformer. Then we have overpressure devices, or what's also known as an SPR, a sudden pressure relay, where it's actually monitoring, similar to a pressure valve, is monitoring though for aggressive changes of pressure inside the tank of the transformer. Same principle, when electrical faults and internal electrical faults occur inside of the transformer, you're going to have this breakdown of oil, which in turn releases gases, and those gases in turn increase the pressure inside of the tank, and this is just a mechanical, pressure relief valve that will activate and in turn will be connected to breakers and so on to isolate the transformer from the system. Under impedance resistance relays are also commonly used to protect transformers from a backup perspective, though. Overcurrent relays are also used to provide backup protection, though, in the case of face-to-face faults inside the transformers. And high voltage fuses, though, are also commonly used for that purpose, though. And these obviously, the concern is that for face-to-face faults, though, enough current, though, has to be present, though, for these elements, though, to detect that a fault does indeed exist. inside of the transformer. So the selectivity of those elements is not ideal. That's why the first three ones, transformer differential protection, the Buchholz, and the SPR, do provide true unit protection, though, for the transformer. In the case of ground faults, though, we could utilize restricted ground fault protection, which we'll discuss in a few slides, transformer differential protection, Buchholz relays, under impedance distance relays, ground over current relays, and high voltage fuses, though, would also provide protection for ground faults. In the case of high impedance grounding, again, restricted air fault protection, sensitive ground fault, sensitive ground over current protection, over voltage protection, and your Buchholz mechanism could also detect these faults. In the case of turn-to-turn faults, when you have turn-to-turn faults, there's no depending on on how many turns are involved. These are going to be faults that may or may not be detected by the transformer differential function. That's why there's new elements and techniques that are used to detect these types of faults, which we'll discuss in a few slides. And then you have your Buchholz alarm that they could assist on identifying these types of faults. And then you could also have the case of a high voltage to low voltage winding flash over. And in this particular case, transformer differential, Buchholz relay, or your sudden pressure relay can provide adequate protection, though, for these types of faults. Now, a lot of these elements that I just discussed, a lot of these elements, though, that we just discussed involved, or the elements that are used to detect internal faults involve differential protection, and that's really the main element as part of any microprocessor transformer protection package. And what we have here, what we're going to use to represent the concept is we have a 3-winding transformer. Okay, take note where the position of the transformer and then the position of the breakers. In the case of depth tank breakers, take note that we're actually taking the outside CT in such a way that the breaker itself is part of the differential zone of protection. So the concept is that during normal operating conditions, if we just assume the power is flowing from left to right in this particular slide, current that flows through this CT or winding 1, it's going to be the equivalent to the current that flows through winding 2 plus winding 3 multiplied by your turns ratio. Okay, so that is the basic assumption. So we are essentially doing an ampere turns calculation, and that should equate to 0. That means that primary winding ampere turns plus secondary winding ampere turns plus tertiary winding ampere turns should equal to 0. And again, the differential zone of protection is defined by the current transformers. So for faults that occurred inside the differential zone of protection, then the current that comes in does not equal the current that comes out of the zone, thus the differential protection should be able to pick up such faults. For faults that occur outside the zone of protection, the current that flows in should equal the current that flows out, thus the differential protection will not detect these types of faults. Okay, so again, basically ampere turns that come in should equal the ampere turns that come out. Now, what are some of the things that need to be taken into consideration? Well, in the case of transformers, okay, as I just mentioned it, though, it's not a current balance, it's not a current balance equation, but it's an ampere turns balance equation, though. And to be able to execute this ampere turn balance equation, we need to have the turns ratio information of the transformer to be able to make this calculation. So in the past, with electromechanical or solid-state relays, we would use what was referred to as tap settings to make this type to provide the relay that information so that the relay would be able to perform this ampere turn balance calculation. In the case of modern microprocessor relays, most of the ones that are available from the major manufacturers, though, they just ask for, you know, voltage ratings, power ratings, and the transformer protection relay itself would be able to determine what the ampere turn balance should be based on the currents that it's injected to it. The second point that is of interest, though, and that needs to be taken into consideration, is the connection of the windings. In the case of a Y-Y or a delta-delta connected transformer, you do not have a phase shift. But in the case of a delta-Y or a Y-delta transformer, you do have a phase shift, and that needs to be accounted for within our differential protection relay. Also, we also need to take into consideration the fact that we utilize CT ratios to step down the current magnitudes and provide them to our relay. So you're going to have different ratios from one winding to another winding. Thus, this is also something that's a source of errors and needs to be taken into consideration. So in this particular case, we have a 69 kV to 13.8 kV transformer, which is delta Y connected, or it's Y delta connected, sorry. All right, let's actually go ahead and take a stop here and address a couple of questions, though, that we have. All right, so I have a question here. Can a sudden pressure relay be triggered by an external fault? You know, again, the sudden pressure relay is really triggered. It's really considered as unit. Could it be? Well, let's explore the principle of how it works. Again, it's essentially monitoring, though, a rapid rise of pressure inside of the transformer, though. And that rapid rise of pressure inside of the transformer, it's usually going to be the result of oil breaking down inside of the tank, which in turn, you know, decomposes into gas, which in turn raises the pressure inside of the tank. That sequence of events can only occur if arcing occurs inside of the tank of the transformer, thus indicating that an internal fault exists. Let's see. Okay, so let's see. We have Y1 o'clock position for third case as well on the slide that I was discussing, the vector, you know, the vector group clock system. Well, it's a YY delta transformer. So Y is at 12 o'clock. The Y connected winding from Y to Y, there's no phase shift. So the secondary winding Y connected in Y, it's also at the 12 o'clock position. And then D sits at 11 because it's a delta connection, though. So there's going to be a 30-degree phase shift from, you know, in relation from the delta to the Y winding. Okay. Let's see, what else do we have? It could be the cost is a high side contribution and low side contribution to the differential is greater than 180 degrees of the acceptable range. And we have a question here. What could be the cost if the high side contribution and low side contribution to the differential relay is greater than 180 degrees? What is an acceptable range? We are seeing 10 to 15 degrees greater than 180. So I can, you know, I can assume, I'm going to assume that what the question is that when monitoring on a transformer that has no phase shift at all from one winding onto the other winding, you should expect 180 degrees, you know, 180 degrees relationship between the high side currents versus the low side currents, and this is because the way the CT polarities are installed. Okay, and I'll explain that in just 1 second with the slide that you have in front of you. If there's any deviations from that, well, you have to take into consideration though that there's not all the current. This is not from high side to low side. You don't have electrical coupling. And what I mean by that is you cannot expect to do Kirchhoff's law from one winding over to the other winding and expect that the current that flows on one winding equals the current that flows on the other winding multiplied by the turns ratio. You need to take into consideration that there are losses involved. So, for example, in this particular case where power flows from left to right, meaning the source is connected to the 69 kV side, there's going to be certain, the current that flows through CT1, through this CT right here, which is a 250 to 5, it's going to have two currents. There's going to be, you could essentially decompose the currents that flow through here in two elements, though. One, which is going to be that due to electromagnetic coupling, it's going to be transferred over to the secondary winding. But then there's another component of that current that is to feed the losses of the transformer. And the losses, or what's known as the no-load current, though, it's usually anywhere between 2 to 5%, depending on the construction of the transformer, how modern it is, how old it is, aged, and so on. So that is a percentage of MVA. So depending on what, depending on what the loading of your transformer is, that may become greater as a percentage of the current that's flowing on the low voltage winding, or smaller, at which point you're going to have the relationship between one winding onto another, though it's going to be skewed more or less significantly. So I hope that addresses that question. Okay. Let's see, what else do we have? We have another question here, which again, back to the SPR, the sudden pressure relay, though. Can a large through-fault near the transformer shake the transformer enough to trigger a sudden pressure relay? Again, it's the sudden pressure relay, though. It's looking for a high rise of pressure, though, within the tank of the transformer. And this high rise of pressure, though, it's not so much a function of the magnitude of current, but it's a function of arcing, the composition of oil, and gases being released inside the tank of the transformer as a result of that arcing. So if, yes, indeed, if the through fault stresses the insulation inside of the transformer in such a way that it evolves into an internal fault of the transformer, then your SPR is going to operate, though. Okay. Let's see, what else do we have? Why CT connection on primary was Y and not delta? We'll discuss in just 1 second, because that's part of the idea behind this example. Okay, so in this particular case, we have a Y-connected CTs on both high voltage and low voltage side, although we have a Y delta connection. So in the case of electromechanical relays, okay, in the case of electromechanical and solid state relays, there was no way that numerically we could recombine the phasors, though, to emulate the delta connection on the low voltage side, so that we could compare, let's call it delta versus delta currents. If we were to just apply a turns ratio or some sort of factor to compensate for the differences between ampere turn balance as well as the difference in CT ratios, we will end up, though, with currents that would be shifted, though, by this 30 degrees. Thus, the addition of the ampere turn balance of will not equal to 0, because we're not properly compensating by the phase shift introduced with the delta connection. So one way that this was resolved with electromechanical and solid state relays was by if you had a transformer whose connection was Y delta, such as this case, then what you would do is your CTs would be connected delta Y in such a way that the currents coming into the relay would be delta delta on each side. Okay. In this particular case, we could see that the currents, the CTs are Y connected, and the currents that are being compared by the relay are phase A divided by CT ratio, B divided by CT ratio, and C divided by CT ratio. And in the case of the secondary winding, we have A minus C divided by the CT ratio, B minus A divided by the CT ratio, and C minus A divided by the CT ratio. And the issue with this is, again, we have this phase shift. So, again, one way to correct for this phase shift is by doing a delta, by connecting your CTs on delta on the Y side, or in the case of numerical or digital microprocessor relays, though, the relays can take this current information. You could program the relay, and you could tell the relay what the vector group of the transformer is, what the CT ratios are, and so on. And the relay will, in essence, emulate this delta connection in such a way that it compares A minus C on both sides, B minus A on both sides, and C minus B on both sides. As I said, on differential protection, you're looking at an ampere turn balance, which is a function of the current and the voltage level, and you also need to compensate for differences in CT ratios. So the way that was commonly done, though, with relays, though, with electromechanical relays, was by calculating tap settings. And the tap settings, for the most part, you would essentially calculate a rated current based on the MVA, highest MVA rating of the transformer. In this particular case, 25 MVA divided by square root of 3 and divided by the voltage level of the high voltage winding. That will give you the rated current. Same thing would be done on the low voltage side. And then those rated currents will be divided by the CT ratio, and that will give you, a per unit value or the tap setting that will be programmed onto the relay. Okay? In this particular case, although the tap settings were calculated correctly, we did not account for the phase shift, for the 30-degree phase shift, which in turn, if you just do per unit calculation, though, this 30-degree phase shift would have resulted in a 52% difference, or 52% or 0.52 per unit differential current, in a way that the relay would have the differential relay would have incorrectly tripped. And here we're just picturing, though, or we're illustrating that phase shift and the need to now connect our high side CTs in delta, our load side CTs in Y, and in such a way that we are now comparing A to A minus C, B minus A, and C minus B on both windings. We are indeed comparing, delta currents versus delta currents, if we wanna call it that, though. But essentially, we have now compensated for the phase shift so that we can properly compare our winding 1 versus winding 2 currents. In the case of 3-winding transformers, though, the same would have to be done on the 3rd winding to compensate for a phase shift, similar to the way that we've done it here. Okay, and here we could see same thing. We're now, we have now calculated our tap settings. Take note now that the high side currents need to be multiplied by square root of 3, and the reason for that is because the delta connection, and in turn, though, this will result in a differential current which will be equal to 0. So again, phase shift or vector group needs to be taken into consideration. Something else that plays out when doing these types of calculations is the tap settings. So tap settings, though, if you're setting up an electromechanical relay or a microprocessor relay that utilizes tap settings, you need to take into consideration the square root of 3 factor, though. Okay. So, as described, differential protection is affected by tap settings, and apply relays, though, that require the nameplate information, though. So some of the things that need to be collected are number of windings, voltage level of the windings, CT ratios, MVA ratings, though, and the vector group. So essentially phase shift, rated current, rated voltage, and CT ratios. Okay, this will allow us to derive our ampere turn balance calculations. And then let's take a look at some sources of false differential current. Well, depending on the winding arrangement, though, one winding will have the capability of, as I said, transformers, delta Y or Y delta connection, isolate zero sequence networks, though, of 2 points of the system, though. So based on this needs to be taken into consideration, because zero sequence currents will be able to flow on one winding, but they on one side of the transformer, but they will not be able to flow on the delta side of the transformer. This represents a sensitivity, sensitivity issue, and something that needs to be taken into consideration. Transformer inrush, CT saturation, over voltages, and so on, all represent false differential currents. Okay, so this right here is just an example, though, of a delta Y bank where for faults on the Y side winding, the Y winding of this particular transformer will represent a source of zero sequence current. However, the delta side, it's not going to be, will not represent a source of zero sequence currents, though, in such a way that based on the way the phase angle compensation is performed, the differential relay, though, may see this as a differential condition or not. So based on the mechanism that your relay utilizes to correct for the phase shift, it's important to take into consideration whether zero sequence currents are being eliminated or not. Inrush current. So when looking at inrush, I'm actually going to come down to a couple of slides to represent, to provide you with this explanation. So if we take a look at this basic, if we take a look at this basic circuit model, though, what your inrush currents, I mean, the concern is, and I'll explain it, from a very practical, in a very practical way. Okay. Imagine that you have a source connected on this winding right here, and there is absolutely nothing connected on this winding right here. If you close into this particular winding, although there's no load connected here, you have this magnetizing branch through which current it's going to flow. That, in essence, is essentially your, inrush current, though, which, if we look at the way we apply our differential protection, there's going to be current that's going to come through winding 1 CTs. Since there's nothing connected on the secondary winding, there's not going to be any current contribution from winding 2. Thus, essentially, whatever current is flowing through the winding 1, it's going to be sensed, or it's going to be interpreted as differential current and as an internal fault occurring inside of the transformer, though. And this is because of this magnetizing branch, though. There are different degrees at which this phenomenon produces higher currents or lesser currents from an inrush perspective, though. The point on wave switching, meaning whether the transformer it's being energized at peak voltage or at zero voltage, though, or at the zero crossing, though, of the voltage waveform. That has a lot to do with it, though. X over R ratio, SIR ratio, and so on. So remnants, though, remnants flux inside of the transformer, though. Those are all things that need to be taken into consideration that will result in more inrush current or less inrush current. But the principle and the basic concern is, as described, you're going to have current that flows through the winding that's associated with the source. There's not going to be any current flowing through the winding that's effectively connected through the load, and that's effectively seen by the relay as a differential condition. And that's again, that's very practical explanation. In this particular case, what we're trying to show here in this slide is we now know that we have this source of false differential current, or differential current. So how can we detect, or how can we monitor for this condition in such a way that we can block our differential algorithm, okay? So that we can block our differential protection, so that we don't misoperate during the energization of the transformer, though, which is where when this inrush current does occur. So one way that this can be identified is by monitoring for the percentage of second harmonics, though. And the essentially the percentage of second harmonics, though, can be, or where the second harmonics come in, though, it's kind of hard to explain with this particular picture. But essentially, what we have here is the following, though. You have a voltage waveform, okay, which is going to be proportional to this blue waveform right here, which the blue waveform is your actual flux, and the flux is going to vary with, the flux is going to be a sinusoidal waveform similar to the voltage, though. And then here, depending on the remanence, or the remanence flux that stayed in the transformer, this particular, the flux waveform is going to be offsetted, though, positively or negative. And when plotted, though, on the BH curve of the transformer, we're going to end up with this inrush current pulses, though, okay, which the way they actually look is they could have very, very high area on the positive plane, or very high area on the negative plane, but not much of a contribution, though, on the negative or positive plane, though, depending on how the flux waveform, though, is shifted. In the case of it being shifted positively, in the case of positive remanence, then you're going to end up with a current waveform that's positive. In the case of negative remanence, then your total flux waveform is shifted down, and you will end up with pretty much all negative current pulses, though. And this current pulses, given their width, is consistent with the footprint of second harmonics. So what we would ABB and other, most major vendors, though, of transformer differential relays, we utilize the percentage of second harmonics, though, to identify inrush conditions. And inrush conditions occur during a couple of examples. They essentially occur each time that you're energizing the transformer, though. And the magnitude of inrush current, again, it's a function of remanence, point and wave at which you're switching, source impedance ratio, and the duration, though, of, it's a function of the X over R ratio. But you could have inrush, though, if you're just energizing a transformer. You could have some inrush currents if you have a closing, through fault that replenishes the voltage at the source terminal of the transformer. Whenever the voltage comes back up to 1 per unit magnitude, you're essentially taking the transformer through inrush. You're re-energizing the transformer, which in turn could result in an inrush type condition to re-excite the transformer. So one way to identify this condition is by looking at the percentage of second harmonics. Another way of identifying this is by looking at doing an integration of the area below the current curve. Okay, so if it's, if the remanence is positive, then again you're going to have a high, significant amount of, you're going to have a pulse, sharp pulse that's going to be on positive plane. If remanence was negative, you're going to have a sharp pulse on the negative plane. But essentially, you could do a ratio of the area below this curve versus the area of the negative curve, and then you could determine, based on that ratio, you could determine whether it's an inrush event or not. Okay? And these are some of the fundamentals, though. The bottom line is that, you know, from a best practice perspective, second harmonic inrush settings, though, are varying to identify that inrush occurs. They really vary from 8% to 15%, and it's pretty important to consult that with the manufacturer of the transformer, since again it's for the most part it's really a function of some random components, such as the point on wave at which the voltage closes and so on, but it's also a function of the manufacturing characteristics of the transformer. Okay, so again, anywhere between 8 and 15%, it's reasonable. The higher on the higher of a setting that you select, then, you know, more likely you are to actually operate during an inrush condition whose second harmonic level, though, was not high enough to be identified. Another element that we have, or another source of false differential currents, is during overexcitation. So during overexcitation, we are essentially based on the voltage level, though, of our transformer. And when we look at this BH curve here, the higher the voltage is, then from a power transformer perspective, not the CTs, but the power transformer, we actually start to saturate the transformer. And for the transformer to sustain EMF, though, as you start to get into this nonlinear region, though, it will require more excitation current to sustain its EMF, though. So what that in turn results in is in more excitation or no low losses, though, that the transformer needs to absorb from the system to sustain its EMF. And the waveform, though, it's a classical fifth harmonic, though, with a high content of fifth harmonic. So again, we could use fifth harmonic or monitoring for fifth harmonic content to block the differential protection during these types of conditions. And again, the issue is, again, with that magnetizing branch, where this is not during the energization. The transformer is already energized and during and under load, but as the voltage on the source side of the transformer increases, the transformer starts to operate in this nonlinear region, at which point it needs more excitation current, though, to sustain its EMF and operate. Okay? Now, from a differential perspective, we, you know, as you're probably familiar with, we utilize differential protection. It's not just based on a particular pickup setting, though, and then if the magnitude of differential current is at that point or above, we trip. There's some errors associated outside of this, outside of the dynamics involved with exciting the transformer. There are some other sources of errors that need to be taken into consideration, though. So some of them are, if you have a low tap changer, though, well, that's something that's a source of error, because when we do our ampere turn calculation, it's a fixed value that we program down to the relay, though, if the relay is not equipped with a mechanism to monitor what the low tap changer is, what the position of the low tap changer is. So if that's the case, well, you need to account for that. You also need to account for the errors on the high voltage and low voltage CTs, though, which C-class CTs have an error, though, of 10%. You have two windings, then, you know, you need to account for that. So that adds up to 20%. And then excitation or no load currents, though, no load current losses, though, again, anywhere between, you know, 2 to 5%, depending on the construction of the transformer. When adding all of these factors, and obviously, you know, you always need a fear factor from a protection engineering perspective, though. So anything from 5 to 10%, it's applicable, though. So you're gonna always end up with a slope setting that's gonna look with a minimum operating setting that's anywhere between 0.3 to 0.4. Okay, if the low tap if your load type changer range is higher, then you need to account for that as well, in turn resulting in higher minimum operating current though. So even though, yes, during normal operating conditions, your differential current should be 0, you need to take into consideration that you have excitation currents, it's going to be 2%. You have errors associated with your CTs. You have errors in your ampere turn calculations because of load type changer. And then you should also always take into consideration a margin. So the minimum sensitivity, though, again, it's going to be anywhere between 0.3 to 0.4 per unit. These are just some sample calculations, though. Ultimately, or generally speaking, you're going to end up with a minimum operating current between 0.3 to 0.4, and then that in turn will result in a slope characteristic, though, because some of these errors are proportional to the amount of current that the relay is seeing of about 35%. Okay. Some modern relays, though, include multiple slopes, and the idea is you know, the higher your slope, the more secure your protection is, because it's going to provide greater error correction, though, to during adverse operating conditions, though. So the idea of having a relay with multiple slopes is first slope, or the flat line up to 1 per unit, provides, you know, good sensitivity for your minimum operating current. Second slope, it's usually on a range between 1 per unit to 3 per unit, which provides good sensitivity and good correction, though, for errors in CTs. And then a third slope, it's usually a slope that's about, you know, 80%, which provides good security, though, for through faults to combat the CT saturation type of conditions, though. So that's why the 3 slopes. The third slope, it's a higher slope that provides, you know, higher error correction. It's not related to the elements some of the elements that we just described, but it's related to CT saturation and how we can go ahead and provide even greater security to ensure that the transformer is not disconnected during such events. Okay? So that is a way of providing differential connection, differential protection, though, for face-to-face and face-to-ground faults. Now let's take a look at restricted ground faults or restricted air faults. Restricted air faults, it's a very, very good element that provides great sensitivity, though, to ground faults inside of the transformer that are close to the neutral point. So the way to look at this is, if you have this is your ground point, this is your Y winding. If you have a fault here at this particular point, essentially nothing happens, okay? And the reason for that is because there's no voltage, though. There's really no voltage, though, between this ground point at that point where you're putting the ground to circulate any current through. As the fault moves up and takes more and occurs at more and more and more and more points and takes more as a percentage of the winding, then the voltage that's going to drive, that's going to complete that circuit becomes higher and higher and higher. Okay? For faults that occur close to the neutral point, conventional differential protection does not really provide adequate protection, because the differential current is going to be very, very small. For these type of faults, adequate sensitive and secure protection is provided. It can be provided with restricted air fault, what we do is we take a look at the direction of the current that's flowing up the neutral and the zero sequence current, though, that's sent by the relay on the line CT. And if a zero sequence, if a fault involving ground occurs outside the zone of protection, current is going to flow up the neutral, and current is going to flow out of the transformer to the fault in such a way that these two currents will subtract and no differential zero sequence currents will exist. If the ground fault, however, is inside the transformer, you're going to have zero sequence currents that are going to flow up the neutral, and you're also going to have zero sequence currents that are going to flow from the system into the transformer. The magnitude is going to be, the magnitude, although small, the directional relationship still combines in such a way that by measuring, though, that differential current, you can detect that the fault is inside the zone of protection, though. So again, this is a great element to provide great sensitivity, though, to ground faults near the neutral point of your Y windings. Another element that's available and it should be taken into consideration is turn-to-turn, negative sequence-based turn-to-turn fault detection. So the best way to explain this is, let's take a look at a three-phase transformer, and a three-phase two-winding transformer, and let's pretend that you have a 10 to 20 turns ratio, okay? Turns relationship. So if on the winding that has 20 turns, you have one particular turn that's shorted, what does that do? Well, you're going to have on one phase, you're going to have a 10 to 19 turns ratio, and then on the other two phases, you're going to have a 10 to 20 turns ratio. It's not really going to cause much of a problem or much of an electrical effect that can really be identified by your differential protection. You will need to short several turns in such a way that the ampere turn calculation that the relay is performing, though, to be unbalanced enough to cause an actual trip. The problem with turn-to-turn faults, though, is that they're really, really hard to detect, though. But now let's take a look at how we can detect these faults, though, using negative sequence element. Well, for a negative sequence, for one of the assumptions of symmetrical components, though, is that your phase A, phase B, and phase C impedance are equal, though. From a transformer perspective, that means that your turns ratio from winding 1 to winding 2 on phases A, B, and C is equal. If you have a turn-to-turn fault, that means that your turns ratio relationship from winding 1 to winding 2 on A, B, and C are not the same anymore. In turn, that means that your transformer has actually become a source of negative sequence currents. So if that occurs, we can actually monitor the direction of the negative sequence current flow to see whether it's inside of the transformer or outside the transformer, like in the picture on the left. And then based on the relationship of those phasors, we can determine whether the fault is internal to the transformer or not. And this is something that has proven to be quite sensitive, though, from this perspective, though. Now, why do we care about face-to-face? Why do we care about turn-to-turn faults, since they don't really result in high magnitudes of fault current? Well, the reason why turn-to-turn faults are very, very important is because even though at the beginning they do not create much damage, they usually evolve and evolve rather quickly. And the reason why they evolve is because if you look at the ampere-turn relationship on a two-winding transformer, winding 1 currents times turns ratio equals winding 2 currents times turns ratio. If you have a turn-to-turn fault, you have effectively created a third winding, in which case all the flux, though, that was linking on multiple turns for winding 1 and winding 2 is now linked to a single turn. That's going to result in a significant amount of current that's going to circulate on that single turn. A lot of current, though, and higher magnitudes of current, higher IR squared losses, high energy that will be dissipated in the form of heat. You essentially now have a huge hot spot inside of your transformer, which in turn could weaken your insulation and evolve onto other faults inside of the transformer. So that's the concern. Okay. In line with thermal effects, it's important to consider through faults on the transformer. So these are faults that do not occur inside of the transformer, but occur downstream or upstream of the transformer. But these are faults that the transformer sees the stress from such magnitudes of current, though. And essentially, this results in the damage curve, which is important, though, to have an overcurrent element that essentially coordinates with the transformer capability curve in such a way that we do not encroach those, we do not thermally damage our transformer, though. And this is a curve, in this particular, the curve in the middle, though, that also needs to coordinate with any downstream feeder or protection, though, that occurs. And as a summary, though, here is just typical protection scheme for power transfer: two-winding power transformer, face-to-face and face-to-ground protection inside the differential zone of protection will be provided by an 87T element. Turn-to-turn protection can be provided by differential negative sequence elements. Face-to-ground protection near the neutral on Y-grounded windings can be provided with restricted air fault differential elements. Sudden pressure relays and your Buchholz will be a form of unit protection, though. From a damage curve perspective, though, as well as backup protection, overcurrent elements, though, should be time overcurrent elements should be taken into consideration, though, as a backup element, though, to your differential protection. Okay, and these should be set in such a way that, you know, a high and a low source impedance ratio needs to be taken into consideration to ensure that the setting and the curve that you come up with will provide proper backup protection. The same applies for your ground overcurrent protection. A 49 element or a thermal overload element should be utilized, though, to monitor the thermal integrity, you know, to monitor the thermal rise inside of the transformer, though this is more of a monitoring slow tripping function, though. But if the thermal capability of the transformer is near to be exceeded, though, it's something that should be taken into consideration. And then an overexcitation as well. An overexcitation element should also be considered if available. What this will do is we'll monitor for your volt-hertz relationship so that we're taking into account the amount of excitation current that flows into the transformer, and we can make, again, slow tripping decisions, though, in regards to that to avoid further damage to the transformer. So this is, you know, pretty standard package that's deployed along with transformers. Now, let me go ahead and take a couple of questions, though, before we wrap up for the day, and I pass it on to Tracy, though, with the, you know, ending remarks. One question is, sudden pressure really operates a rate of change of pressure rather than just change in pressure. Yes, it's a rate of change of pressure. So it's a rapid change of pressure, though, that will in turn trigger the SPR. That is correct. There are some, but it's, you know, one of those gray areas. Slides refer to presentation. I have a question here. Can the slides be provided for the presentation? Yes. Presentation as well as a recording of the presentation will be provided. Yep. We will, another one. Yes, the slides will be provided to the presentation. We have a question here. Is it a good idea to block sudden pressure relay operation during large through-fault currents of the transformer? Again, you know, the fact is you're looking at on the sudden pressure relay, you're looking at a rapid rate of change of the pressure inside of the tank, which is usually associated with arcing, which in turn results in oil decomposition inside of the transformer, thus releasing gas. So through fault that does not have any electrical consequences inside of the transformer, though. Even though there will be mechanical effects, though, inside of the transformer, though, for the most part, it should not operate your SPR relay. Then I have a question here. Please, can you tell us about standard for average values of inrush current? This is a parameter, very complicated to find. Yeah, indeed. I mean, just here, and I'll go back, and for this question, you know, a lot of the times we really need to look at things from a basic circuits perspective, though. So, if I go back to this picture right here, okay, and just go ahead and forget everything that's from where the mouse is to the right, okay? Imagine that that is an open circuit, okay? So, if we assume worst case scenario, what you're going to have is to the left, you're going to have a source, you're going to have a source impedance, you're going to have the primary winding impedance, which again is the leakage inductance of the winding plus resistive losses of that winding. And let's say worst case scenario, though, you essentially have a short circuit, though, between this point and this point. You're essentially short-circuiting the magnetizing branch. If you go ahead and do that particular switch at voltage equals 0, okay, then you're going to offset that particular current magnitude, though, by square root of 2. So, you know, theoretically, your absolute worst case scenario, though, cannot get any worse than that, okay, because you're essentially completely disregarding the magnetizing branch of your particular transformer, though. So, you know, big part is your sourcing, you know, your source impedance. It's obviously what for the most part is going to regulate what that inrush current is, the point in wave, which again is something that is random. Now, if the question is more in regards to the amount of second harmonic content, again, that is really something that the manufacturer of the transformer is the one that needs to provide that information, because that's really primarily a function, though, of the material and the type of construction that was utilized on the core, which in turn is the primary, you know, the primary parameter that affects how this branch behaves. All right, so we're really out of time for today. I'm going to go ahead and pass it on to Tracy, though, for the closing remarks. So thank you very much, everybody, for the opportunity and participation.
That concludes our presentation for today. The next webinar is Line Distance Protection on October 12th. You will receive an email following the conclusion of this webinar with a link to the online